Hi everyone. So we're finally ready to talk about what happens when you try to do a Fourier series of a function that is not periodic. And we're going to motivate that in part by thinking that breaking functions apart into complex exponentials makes it very easy to understand what's going on with the function. That you have these frequencies that you can use to build a function back up again. And in the same way that if we have something that's periodic and we can reconstruct it from its frequency spectrum, it would be nice if we could do the same thing with a function that isn't periodic. So this theory is useful enough that we want to be able to extend it to functions that it's not obviously applicable to. And that's where the idea of the Fourier transform is going to come in. Now, the Fourier transform is really the object that is ubiquitous across an enormous swath of engineering and science applications, because the idea of the Fourier transform is that you can cover periodic functions with the discrete Fourier transform, which is what we've already done when we found the Fourier coefficients, and non-periodic functions using an integral version of that, which we're going to develop right now. To motivate what we're going to do, we're going to look at the spectrum of a specific function. So there's a really important signal type function that comes up in a lot of applications called the rectangle function, and it has this graph. It's 0 until it gets to negative 1/2. Then it pops up to be 1 for a while. And then it drops back down again to be 0 from 1/2 to infinity. And it's important here that the area underneath this square is finite. So we're going to be using periodization on this thing to sort of figure out how we can develop a Fourier series for it, or an approach to something like a Fourier series for it. So the usual notation for this function is something like rect t, or you might see pi t, right? Where the pi is supposed to represent that you go up and then down again. All right. So the formal definition of this is that f of t is equal to 1 when the absolute value of t is less than 1/2, and 0 when the absolute value of t is greater than or equal to 1/2. It doesn't really matter where the dots are for us. In other applications, it does matter, but that will be specific to whatever field you happen to be in. So this function is not periodic, but I would like to come up with some way of describing it like it was periodic. And so what I can do is I can look at the periodization of pi of t. And remember that the periodization is that function g of t, which looks like the sum from n is equal to minus infinity to infinity of pi of t plus n capital T, where t is the intended period. So we did this on a previous homework assignment to construct I think we did the triangle function and its periodization. So the tools that we're going to try to use here, given that we can make a function of any period that we want, are that we know that we can write down the Fourier series for a function of period t. Using the ideas from the previous homework, which were that we write f of t is equal to the sum from n is equal to minus infinity to infinity of cn e to the 2 pi I n little t over capital T. And then we calculate the cn's by doing 1 over t times the integral from 0 to t of f of t e to the minus 2 pi I n t over big T dt. So this is the approach that we take when we're trying to do a Fourier series for a function that does not have period 1. Okay? So the idea that we have maybe is that somehow we can take this formula and we could let the t go to infinity. That is, we could let the period of the function, we could pretend that the period of the function just keeps going and going and going forever. And so for any value of t that we choose here, when we periodicize the rectangle function, we're going to be able to write down a Fourier series for it and find its Fourier coefficients. So that's the next thing that we're going to do. I'm going to show you some examples of what this looks like for different values of t, And then we're going to compute a formula for the Fourier coefficients when this function has been made to have period t. So let's draw what that looks like first. So t equals 1 is not a very interesting case because the rectangles all pile up on top of each other. So let's look at capital T is equal to 2 for the periodization of the rectangle function. If you did the periodization exercise, you should see that this function is going to repeat itself every 2 units. And what I mean here is that it's going to go along until it gets to 3/2 and then pop up and then come back down again. And then it slides out until it's at 4, and then it pops up and comes back down again. And that's actually what the t value that you've chosen does. Since t was equal to 2, this rectangle is going to repeat itself every t is equal to 2 units. So it has period 2 because it takes that initial shape and just shifts it by 2 and then shifts it by 2 again and shifts it by 2 again. So whatever the initial shape was just gets pasted down over and over and over again with that period. If t was equal to 4, then the periodization is going to come in. It's going to have a rectangle in the middle like usual, but now the next rectangle does not appear at 2, it appears at 4. So this function has double the period. Okay. So the idea that we have here is that maybe what we can do is, if I'm just interested in studying the Fourier series for this thing right in the middle, maybe what we can do is we can spread these rectangles on the outside away and away and away and away, and see if that's going to give us any information about what happens to the spectrum of this middle thing, the Fourier coefficients of this middle piece. So we think of sort of t is equal to infinity. This is our hopeful idea, is maybe what we can do is we can set up a graph where we have the function we're really interested in the middle, and then we just shoot the other rectangles out to positive and negative infinity. That's what it would mean to send this period equal to infinity, would be that instead of rectangles sitting right here, they just slide out and out and out and out until they disappear. So that's the idea, is hopefully we can somehow come up with an expression for the spectrum in a case where I can do that in a well-defined way, and then use a limit to see if we can recover what the Fourier series for this thing, or the spectrum of this, would look like in the case where it's not a periodic function. So we're going to use the periodization of this function to try to come up with an expression for its non-periodic form. So let's just assume that we have some fixed t value. So we fix t. And then we can write down the periodization of the rectangle function by writing g of t is equal to the sum from n is equal to minus infinity to infinity of the rectangle function of t plus n capital T. I want to be able to compute the Fourier coefficients of this periodic function over one period. And that means that I could write down that Cn is equal to 1 over t times the integral. So I just need to integrate over one period of the function. And it does not matter if I integrate from 0 to t or if I integrate from minus t over 2 to t over 2, as long as I'm integrating over one period of the function. And in this case, it's going to be simpler to integrate from minus t over 2 to t over 2 because the function is only defined from minus 1/2 to 1/2. And so I can keep the interval altogether. Now, the very first thing that I can do is, because this function is only defined from minus 1/2 to 1/2, I can immediately reduce this integral to the integral from minus 1/2 to 1/2 of, well, what is the value of g of t on the interval? It's just 1. Because remember, what g of t looks like is it just pops up and does a rectangle between minus 1/2 and 1/2. And then it's 0 again until we get to the next period, and then it pops up and does another rectangle. Okay, so this integral is always just going to exist from minus 1/2 to 1/2, no matter what. All right, so now we just continue with the integration. So we've already reduced this to Cn is equal to 1 over t, the integral from minus 1/2 to 1/2 of e to the minus 2 pi I n t over t dt. And then if we grind out this computation, you just do the typical exponential thing where you do 1 over minus 2 pi I n. And then since there's a 1 over t in there, then the t pops up in top. E to the minus 2 pi I n t over t evaluated from minus 1/2 to 1/2. And what you end up with is, well, the t's cancel, and you get 1 over minus 2 pi I n e to the minus pi I n over t minus e to the positive pi I n over t. And there's a 2i right here. And this, to me, looks an awful lot like a sine function, because remember that the sine of theta is equal to e to the I theta minus e to the minus I theta over 2i. And so living inside here, I've got a theta and a minus theta and a 2i, and there's a negative here which would kill this negative inside. And so all of this just turns into the sine of pi n over t. And in front, we have a 1 over pi n. So here's where we're at. We know that if we take the rectangle function and then we calculate its spectrum and we evaluate that spectrum at the points n over t, which is where the frequencies are, then we get this formula for Cn that we just produced. So what we mean is that the spectrum of the t periodic rectangle function at a frequency n over t is equal to 1 over pi n times the sine of pi n over t. And at this point, you might think, okay, great, we've got a spectrum of this periodic function. If I let t go to infinity, then that should recover that curve that we looked at, that where the points of the spectrum lie. The problem is that I can't just let t run off to infinity yet, because if I try to apply it to this, I'm going to get 0 out everywhere. Every Fourier coefficient will look like 0. So there's something else we have to account for, which is that as we take the periodic functions and we make them larger and larger and larger, the power of each individual frequency diminishes, because it's like the energy of the function is being spread out thinner and thinner. And that shows up in the limit, because the sine of 1 over t basically acts like 1 over t. As t goes to infinity, those go to 0. This is one of the most famous inequalities or approximations in mathematics, that the sine of an angle is equal to the angle for very small angles. And so if I want to adjust this so that all of that frequency information just doesn't disappear completely, I have to scale the answer in order to take the limit. So I have one more step to go. To keep all of the frequencies from disappearing, I have to introduce an extra factor of t. So we'll call that the scaled spectrum of a t periodic function, pi of t, which is the rectangle function, evaluated at n over t is equal to t times pi times, 1 over pi n times the sine of pi n over t. And this extra copy of t right here keeps all these coefficients from just disappearing if I took a limit as t goes to infinity. Now, it turns out that this is pretty nice, because this number right here and this number right here are identical to each other, right? Pi n over t, and then there's a pi over n over t on the outside. So you could rewrite this as, this is wordy, the scaled spectrum of the t periodic pi of t applied at n over t is equal to the sine of pi n over t over pi n over t. And this is a really special function. So if we let s be equal to n over t, and the motivation for this is n is an integer, and t is an increment that's making those numbers smaller and smaller and smaller, right? As t gets huge, n over t gets smaller and smaller and smaller. And so in the limit, as t goes to infinity, if I let s equal to n over t, this is almost like s being a continuous variable. This is the same as when we move from delta x to dx. So I think of s as sort of the continuous version as t goes to infinity. Then this function right here looks like the sine of pi s over pi s. And that function is so ubiquitous it has a special name, which is sinc. Comes up all the time. So what we're hoping is that maybe this process that we did here, where we started with a function and we ended up with this continuous version of the function at the end, right? That this thing right here is what we're hoping is the scaled spectrum of the t periodic rectangle function after we let t go to infinity. Then we get this. And that thing right there, that is the continuous spectrum of a non-periodic function. So this thing right here is what the spectrum of a function looks like. That is, the Fourier coefficients are not just a bunch of dots anymore. They're a continuous function where every possible real number appears as a frequency. And if you plot that function, what you end up with is the curve that illustrates the dots. So back over here in the book, once you actually compute the sinc function, which is right here, and you plot it, you get that curve that dictated where the spectral points for the discrete case landed. So that is the limiting curve to the situation we looked at right here, where we computed the spectrum or the Fourier coefficients of the t periodic function for different values of t. And the bigger we made t, the closer the dots got together. And then we finally figured out how to scale it so that if we let t go to infinity, we end up with a solid curve that comes out the other side. Let's see if we can write down what we did here in an integral formula that might show a process for getting from where we started to, that is writing down this t periodic function, to where we ended up. So what we showed was that the scaled spectrum of the function f evaluated at points n over t was equal to t times the Fourier coefficient cn, right? We were working with a specific case of cn's, but this is what we did. We calculated a formula for the Fourier coefficients at n over t, and then we multiplied it by t to scale it to make sure that the Fourier coefficients didn't disappear, and then we took a limit. Well, this is equal to t times 1 over t times the integral from minus t over 2 to t over 2 of f e to the minus 2 pi I n little t over t dt. But the t and the 1 over t cancel. Remember, this is just, that's the definition of Cn, right? That's the formula that you use to calculate a Fourier coefficient for a function of period t. Then the t's cancel, and you end up with an integral from minus t over 2 to t over 2 of f times e to the minus 2 pi I n over capital T little t dt. But n over t in the limit, that's the thing we called s. And so if I take a limit as t goes to infinity, I get the integral from minus infinity to infinity of f times e to the minus 2 pi I s t dt. And this object right here, that is the Fourier transform of f. And we usually write it something like script f of f. And the variable of the Fourier transform of f is not t anymore because the t disappears in the integral. It's a function of s. So we Fourier transform a function from the time domain into the frequency domain. And if that function is not periodic, this is the formula that we use. The Fourier transform of f evaluated at s is equal to the integral from minus infinity to infinity of f of t e to the minus 2 pi I st dt. And what that does is it produces a spectrum, which you can think about as being the Fourier coefficients for a non-periodic function. And another notation for this that corresponds to what we've already done with Fourier coefficients is we could also call that f hat of s. In either case, what this means is we take this integral formula, we apply it to a function f, and what's produced is something that represents something like the Fourier coefficients, except now it's continuous and not discrete. So now that we have the Fourier transform, that is, we got a formula for taking f and turning it into f hat, we want to know how to go backwards. If I'm working with a periodic function, if I start with f, then I can write down that the Fourier coefficients Cn are equal to the integral of 1 over t minus t over 2 to t over 2 f e to the minus 2 pi I n t over t dt. I can compute them all. And that gives me a function f hat of n is equal to Cn. And it's easy to go backwards. This is called analysis. If I start with f hat of n, I can always put f back together again. This is called synthesis, by just taking the right harmonics and multiplying them by fn. Then I can define a function f of t is equal to the sum from minus infinity to infinity of f hat of n e to the minus 2 pi I, e to the positive 2 pi I n t over t. If I have the coefficients, I can build the series. If I have the function, I can find the coefficients. Okay, so I can go back and forth. So I can do this direction with the Fourier transform. I can do that direction. We just shown how to do that. If I have f which is periodic, or sorry, if I have f which is not periodic, f not periodic, and I start with f, well, then it's easy to write down f hat of s just by using what we just did. I apply the Fourier transform to f, and what I end up with is its spectrum. The integral from minus infinity to infinity of f e to the minus 2 pi I s t dt. How do I go backwards? This is, I mean, the point of the spectrum is if once I've pulled something apart into frequencies, maybe I can adjust those frequencies and then put it back together again. How do I do synthesis in this case? The answer is I can define something called the inverse Fourier transform. And it turns out in the same way that in the discrete case, this has an e to the minus 2 pi I n t over t. So when I'm finding the coefficients, I go one way. And when I'm putting the function back together again, I have to build it up in terms of the harmonics that those coefficients go with. The inverse Laplace transform is built exactly the same way. If I want to start with an f hat of s, which is not a discrete thing anymore, it's a continuous function, and I want to take that continuous function and turn it back into the function f that it originally came from, I have to apply something called the inverse Laplace transform. And the inverse Laplace transform builds f of t by integrating from minus infinity to infinity of the Fourier coefficients times the harmonics they apply to, e to the 2 pi I st ds. So this is the synthesis step when we're working with the Fourier transform. So the Fourier transform takes functions in the time domain and spits out functions in the frequency domain. And the inverse Fourier transform takes frequency domain functions and puts them back into the time domain. This integrates away the t, this integrates the s. This is exactly corresponding to the discrete case, where when I want the coefficients, I pull them apart in terms of the conjugate of these harmonics. And when I want to put them back together again, I have to multiply the coefficients times the harmonics they correspond to. That's exactly the same thing here. Here I am computing coefficients by multiplying by the complex conjugate of the harmonics they correspond to in sort of an inner product. And here I am taking those coefficients and multiplying them by the harmonics they correspond to. And then I have to integrate instead of add because s is continuous and not discrete. So capital F of f, which is f hat of s, is the integral from minus infinity to infinity of f of t e to the minus 2 pi I st dt. And I can come back from an f hat, which is an f of t, by writing down the integral from minus infinity to infinity of f hat of s e to the positive 2 pi I st ds. Okay. And the beautiful thing about this is these are inverse operations. F of f inverse of f is f. So the transform of a transform is the original, the inverse transform of the transform is the original function. And that's the thing you really want if you're moving problems from one domain to another to make them easier. So let's look at an example of a Fourier transform of a function, and then we'll talk about an application of this particular one. So let's compute exponential decay. So let's suppose that we had the function f of t was equal to e to the minus at, where t is positive and a is positive. Okay, and we're going to let it be equal to 0 when t is negative. So this is just a positive time exponential decay. Its plot looks like this. You start here, and then you decay like this. So one-sided exponential decay. Okay, well, that's not a periodic function. And so if I'm going to try to compute its spectrum, I have to use the Fourier transform. So let's look at the Fourier transform of f. So by definition, the Fourier transform of f is the integral from minus infinity to infinity of f times e to the minus 2 pi I st dt. But because this function is only defined, or is only non-zero between 0 and infinity, I can immediately rewrite this as the integral from 0 to infinity of e to the minus at, e to the minus 2 pi I st dt. So the Fourier transform of f we have written down as the integral from 0 to infinity of e to the minus at, e to the minus 2 pi I st dt. So I can combine these together and I'll get e to the minus 2 pi I st minus at. T factors out of both of those. E to the minus 2 pi I s minus a t dt. Now this is an improper integral, so I should probably set that at n and take a limit. When you do, you're going to get the limit as n goes to infinity of 1 over 2 pi I s minus a times e to the minus 2 pi I s minus a t evaluated from 0 to n. At this point, you plug in the limits of integration and take the limit. When you put in n, what's going to happen is you're going to get an e to the minus infinity, which will turn into a 0. When you subtract off plugging in 0, you get a minus 1, but then the minus 1 is going to cancel these minus 1s down here, and you just end up with 1 over 2 pi I s plus a. So there you go. That right there, that's the Fourier transform of the exponential decay function. So the Fourier transform of the one-sided exponential decay is equal to 1 over 2 pi I s plus a. And this function is a complex valued function. If you're interested in visualizing what this looks like, then we can plot it, but we can't plot the function because remember, complex numbers consist of a rotation and a magnitude. But we could plot the magnitude of this function. So if we want to plot the spectrum, common practice is to plot the square of the absolute value. And that's called the power spectrum because it represents how much energy is contained in the signal at different frequencies. And that means that we write down something like the absolute value of f hat of s squared, which in this case is the absolute value of 1 over 2 pi I s plus a squared. And if you look at that for different values of a, you get families of functions that look like this. So these functions right here correspond to these exponential decays up here. And for different values of a, you get different frequency plots. Remember, that's not the whole frequency. All we're looking at here is the energy contained in these frequencies for different frequencies. So we're looking at the square of the magnitude, which means we're not talking about phase. However, I can still see what the distribution of energy in the signal is and what frequencies are the very strong frequencies. And it turns out to be the case that this particular function shows up in some really interesting places, like, you know, these plots where if you actually plot these densities, so you plot this out and you get curves that look like this, they're not Gaussian curves. They kind of act like that where they dive off at the sides. But these actually turn out to predict things like the probability of electrons leaving excited energy states and where they tend to land once they leave. So this is the sort of thing that comes up in chemistry or photovoltaics, for example. So where are we at in total? If I have a periodic function, f, of period t, I can compute the spectrum by writing down f hat of n is equal to the integral from 0 to t, 1 over t to normalize the interval, and then f e to the minus 2 pi I n t over t dt. That's how I compute the coefficients. If I want to put the function back together again, then I could write down that f is equal to the sum from n is equal to minus infinity to infinity of f hat of n e to the positive 2 pi I n t over t. This is analysis. This is synthesis. If I have a non-periodic function, I have exactly the same theory. If we have a non-periodic g of t, then I can write down the spectrum f hat of s is equal to the integral from minus infinity to infinity of f e to the minus 2 pi I st dt. And if I want to put the function back together again, I can write down that f of t is equal to the integral from minus infinity to infinity of f hat of s e to the positive 2 pi I st dt. And the notation that we use for this is the spectrum is the Fourier transform of f, and the original function is put back together from that by using the inverse Fourier transform of f hat. This is the synthesis, or this is the analysis, or decomposition, and this is the synthesis. All right, so that's our entire theory of Fourier transforms now. Now we can handle every function with this methodology. So this is where we're at, and as far as we're going to go with the development of the theory of Fourier series, with the exception of one really powerful algebraic relationship that functions have with their Fourier transforms called convolution. Convolution is a way of taking really complicated interactions in the time domain and turning them into multiplications in the frequency domain. So it turns out that multiplying frequencies together in the frequency domain actually has a very easy to understand relationship in the original time domain signal. And engineers use that all the time to modify signals. If I know over here that I can multiply by a function and change certain frequencies, then I can predict what happens to the time domain signal on the other side by going back through the Fourier inverse transform. Where we've arrived at is kind of the foundation for how the Fourier transform is used in all of the areas that it's used in. So you should try to compute a couple of examples. I'll give some examples to do on the homework this week of working through how to compute the Fourier transform of very simple functions. But the big idea that I want you to have in mind is that the Fourier transform takes something that's happening in the time domain, some kind of signal that's telling me the height of an object at time t, and transforming it into what oscillating frequencies were present in the original signal. And they're there even if they don't look like it. That's basically the lesson of the Fourier transform, is that even functions that are not periodic are built out of periodic signals. And so if they're built out of periodic signals, then we can manipulate those frequencies or understand a function in terms of those frequencies. All right, practice hard. You're going to see this again and again and again. The Fourier transform is everywhere. Some of the examples that I put up in that big example post show some of the directions that it gets taken. It's one of the most powerful ideas in mathematics, and thematically, it is indicative of a major abstraction, which is if you're working on a problem in one type of variable, and that problem can't be solved, so say you're working on a signal in the time domain, you just transform it into a different problem, solve it over there, so work on it over here in the frequency domain, and then you pull it back over with the inverse transform. So shifting domains to solve a problem and then coming back to the original domain is one of the key themes of all of applied mathematics. Okay, work hard. See ya.